as we move on. Okay, so today it's our great pleasure to invite Dr. Qingkai from Berkeley. And Qingkai spent his early study in China, majoring in civil engineering before he started his PhD at geophysics at UC Berkeley. Then he continued his work as a researcher and then as a researcher faculty. Now, currently, theoretically speaking, I think currently you are a visiting researcher at Google. Although I say, no matter where is your institution, you are working at home anyway during the epidemic.
Right.
So today, Qingkai is going to share of his work that he has been working on for a couple of years about how to use the smartphone to detect earthquake from the Seismo Lab in Northern California. Okay, with that, I will give the rest time to Qingkai.
Sure, yeah. First of all, thanks for inviting me. So it's my pleasure to give a talk here. So yeah, just to give you more introduction about myself. So I'm currently a researcher at Berkeley, as Professor Zhang just mentioned. And right now I'm also visiting Google as a in their visiting faculty program. Basically, we are trying to turn our research project into a product at Google so that every smartphone, as long as you have an Android system, that will become a seismometer. So this is like what we are working on there. So I will give you an overview of the project I'm currently working on. So this is the project that actually I worked on in the last maybe 8 or 9 years. I actually started with my PhD. It's called MyShake. So when I started my PhD at Berkeley, so we decided to start with some like a project that we can have more detecting sensors to detecting earthquakes. So we asked ourselves what kind of things that we can increase our density of our seismic network stations. So smartphone is one of the options. So I decided to take this task and turn that into my PhD thesis. So I worked in the last few years to make a prototype, and now we have a system that can detect the earthquake. And now we actually move more forward and to collaborating with Google to try to implement all these things into a global scale network. So this work, actually, I mostly will focus on MyShake and to touch on a little bit of the Google system that we just launched a few months ago. So the MyShake work actually is funded by like UC Berkeley and also Moore Foundation. And recently, from last year, OES, that's the California Office of Governor's Office of Emergency Service, actually also funded MyShake to be the official early warning app in California. So basically, this app, as long as you can download, and then it turns your smartphone into a seismometer. And at the same time, if you are in California, you will start to get early warning messages whenever there's an earthquake near you. So I will talk more in details. By the way, feel free to stop me if you have any questions. So let me start to introduce the team. I think let me just make this smaller so that you guys can see. So this work actually started with I'm the only one worked on this project before as a PhD, but then now it's growing into a big team that we have actually 2 branches. One branch is the developers, which is develop the app and the backend and so on, and also maintain the whole system. And the other team or branch is like research. So basically, the PI is Professor Richard Allen at UC Berkeley, and I'm the researcher, mainly oversees the development of the research part. And also our former PhD students and postdoc and current PhD students are the main forces doing the research on the MyShake side. So let me see, it's not moving. So we know that when we use smartphones and when we turn the orientation of the smartphone, the screen will change with it automatically. So this is all because there's a sensor inside the smartphone can sense the acceleration, basically can sense the gravity, which direction is gravity, and then use that to turn the screen so that you can see this like automatically orientation of the screen. This is actually very similar to what we used in seismology. So basically we use the seismometer to detecting the ground motion the similar way as well. So that's why initially we thought we can use this to detecting earthquake. And then this is basically saying that if we can turn everyone's smartphone into a seismometer, we will have a very large dense seismic network globally. So that's the initial part of the system or the idea of the project. And then, so we need to see whether it can record the earthquakes. So this is actually some recordings I recorded before, like this is actually my phone. I'm taking bus. I was taking bus. I was like running. I was walking. I was put the phone on the desk because we know that we use phones differently. So we needed to determine when the phone actually recorded the earthquake or it is recorded like some human noises. So this is also an earthquake signal that recorded on my phone. I think this is the magnitude 6 earthquake in 2014, actually about 40 kilometers away from Berkeley. So this is the Napa earthquake. It occurred in the middle of night and woke me up. So, but at the same time, the phone on my desk actually recorded this signal. So you can see the 3-component acceleration. Earthquake actually arrived at Berkeley around this time. And then it's basically like shaking the whole area, like you can see the amplitudes on each of the component. So basically this is the idea that we can use the phones to detecting the earthquakes. And if we can filter out the human activities as I show here, then we can actually have a more relatively accurate way to determine whether this is due to earthquake or this motion is due to human activities. So if we look at the hazard map globally, so this is basically showing you the global hazards with more, like warmer color means more earthquake hazards. And you can see a lot of the places there are like a very high earthquake hazards, but in terms of seismic stations, there are not so many of the dense seismic networks. So this is basically saying that if we look at the magnitude 7.9 earthquake in 2015 in Nepal, so it caused like about 8,000 fatalities, but like in terms of seismic stations, they only have a few seismic stations in their nation, but there are about 6 million smartphones. And that's why we think if a small fraction of that can be used for detection, that will be really great. So this is actually our motivation that at places where they don't have seismic networks, we can have the dense seismic network using only smartphones. So let me give you some overview of earthquake warning system. So you may have heard of this before, but if you are not, so it's basically a very simple system. It's more like what we saw in the thunderstorm. Like usually we first see the lightning first before we hear the sound. So this is because the two types of waves during the thunderstorm, like the lightning basically travel at the speed of light, and the sound and the thunder sound is basically travel at the speed of sound. Like these two waves travel at different speed. So at distances, so you will see basically they arrive at different time. So the faster one, of course, is the light travels first. So this is the idea of behind the earthquake warning system. During the earthquake early warning, during the earthquake occurs in one region, if we can detect the earthquake really fast using the sensor, we can actually send the signal using the electronic signal travels at the speed of light to warn people in the cities. For example, so this is the California Shake Alert system, which is the early warning system using the traditional sensors. You can see the traditional sensors here. And during the earthquake generates two types of waves, like a P wave and S wave. I assume everyone knows about the P and the S wave from their introduction to the earth science. So basically all these waves travel at the speed of sound, roughly like a speed of sound. So you can see if we're detecting this at this sensor here, we're detecting the earthquake, then we can send a signal back to the city, like the target city we want to protect. Basically, like this is travels at the speed of light, and this is travels at the speed of sound. So when the warning message arrive at the cities, so at some places, like they even even give them like a few seconds before the seismic wave arrive there. So this is actually the early warning system. Usually it takes about like usually for the warning time is around like seconds to minutes. I think in magnitude 9 Tohoku earthquake, 2011, Tokyo actually got like a 60-second warning before the strongest shaking starts at the city. So the idea of using smartphones is that we can have more smartphones to detect the earthquake. This will improve our speed of detection. That's like give us more warning time. And also a lot of the times, if there's no seismic stations at countries like Nepal, so this smartphones network can work as the standalone seismic network. You may ask, like a few seconds warning, how that can be useful. So if you think about like a lot of the automate systems, actually it's very useful if you know a few seconds ahead of time. For example, high-speed trains can slow down the train to basically to decrease the risk of derail. And also like for some very precision operations, for example, like a surgery at the hospital, you don't want the doctor actually working on someone's body during the earthquake, right? And also during the earthquake, we don't want the flight to land because like it may just crush the flight and causing a very bad accident. And also for some type of work, a few seconds warning can even let this like a construction worker to work to a safe place, so that's like basically save lives during this situation. So this is why earthquake warning is really useful. And so basically we think that these smartphones can help to improve the system to basically to increase the warning time and also help to estimate the magnitude and intensity better. So this is actually a diagram how we designed MyShake. So basically you download the MyShake app on your phone, and each phone will become a seismometer running in the background to determine whether you are experiencing an earthquake or you are experiencing some human activities. And whenever these phones detect something like an earthquake, it sends data back to our central server, which is in the cloud. And in the central server, we actually can determine whether this is a real earthquake or not, based on like the aggregation of information from all the phones. And also at the same time, we also save the data, about 5 minutes worth of waveform data from all the phones things they detected earthquakes, and for further analysis and also for other seismological applications. there's a lot of algorithms actually back up the MyShake system, which really enable the whole detection parts and to detect the earthquake fast. So I will introduce all these algorithms one by one, give you a high level overview. But here I just briefly mention which parts we use which algorithm. So on the phone, you just saw that we use the phone differently, like running, walking, and so on. So we actually implemented artificial neural network approach running on the phone in real time to determine whether the movement of the phone is due to earthquake or not. If it's due to earthquake, it sends data back to the cloud server. And at the cloud server, we actually have a real-time clustering algorithm to cluster the data we collected from all the phones and to determine whether this is earthquake or it is just some random signals. Because if you think about like one phone can detect some earthquake, but if in a real earthquake, so usually you see a very broad like triggers of the phones during the real earthquake. So that's why you will see some like a spatial and temporal clusters during the real earthquake, but not during the daily activities. And then based on the data we collected from the phone, there's a random forest. Basically, it's a tree-based nonlinear estimation of the magnitude of the earthquake based on where is the distance of the phone from the epicenter and also the amplitude of the shaking. And at the same time, we save the data like the three-component acceleration data, and these waveforms can do other type of activities, seismological applications, as what we already done in the traditional seismology. And also on the back end, we also implemented like a convolutional neural network to further determine whether this waveform is due to earthquake or not, because we have the luxury on the back end to use a longer time window instead of like on the phone in terms of like a detection speed. We only use 2 seconds time window to detect that so that we can detect the earthquake fast. So this is how the overview of the system. Let me enter into like each one of them to give you more details on the algorithm. Like I've said, like we do all kinds of activities with our phones. So if we record any signal like this, how do we know whether this is an earthquake or this is just something else or like human activities? So that's why we need to design an algorithm that to determine this movement is earthquake or this movement is human activities. So, very high level introduction of the artificial neural network approach. So think about like when we were kids and we try to learn the objects like apple and orange. So our parents gave us like these two objects, apple and orange, and we start to sense the objects, right? Like a color, texture, smell, and shape, and so on. So these are called features in machine learning. Basically, you can think to characterize the difference between different objects. And then we remember these features in our mind. And the next time when someone gives you another object, you can determine whether this is an apple or orange by comparing the objects you already know. Sometimes you'll make mistakes, like maybe someone gives you a green apple, you think, okay, this might be an orange. So, but your parents will tell you, no, this is still an apple. So you will update your model like based on the features. Okay, green color, texture like this, or smell like this, it's still an apple. Basically, you will update your model in your mind to next time when someone gives you another like a green apple, you will not make any mistake. So this is the way, we actually learn the objects, or classify the objects in the real world. But this is also similarly done by the artificial neural network, that we extract the features from the different objects and then determine whether this is due to earthquake, due to non-earthquake. So this is like exactly the same thing that we are doing. So to be more specific, for example, we showed the human activities like I recorded before, like this. We showed the earthquake signal, and by eye you can see the difference between them, like in terms of the periodical signal, in terms of the amplitude, in terms of the general shape, and so on. Now we need to capture these features that best characterize these two types of motion. One is human motion, one is earthquake motion. So what we have done is that we actually use a sliding window, 2 seconds sliding window, to slice through the whole, like a time series of the movement. And in each of these window, we actually extract the features like we just showed in the apple and the orange example. We just extracted like the features we think that can characterize the earthquake and non-earthquakes. So basically, we scan through the whole window, the whole waveform of the time series, and then we extracted the features. So this is just some features I extracted. So we tested 50 different features, and this is like some of them are time domain signal, some of them are frequency domain signal, some of them are statistical features. So all these features we extracted, then we chose like a subset of these features that best characterize the earthquake and non-earthquakes. So let me see if I can move this one. So basically, this is the two most useful features. One is the frequency feature, the other is amplitude feature. And each of these dots here showing you either this motion in the 2 second window is due to earthquake or it's due to non-earthquakes. So you can see the blue ones are the non-earthquakes, the red ones are the earthquakes. So you can see it's actually also easy to explain the physics. So you can see that like for the earthquakes, usually it's a very broader in terms of frequencies. You can, but the amplitude is relatively like in the middle part of this figure. But for human activities, so you can see when there's a lot of the dots actually have broader frequency contents, but very low amplitude. So this is basically means that you put your phone on the desk and it records random noise, but the amplitude is really low. Or there's some like very large amplitudes here, but like the frequency are really low. So basically low means that like the phone moves relatively slow. So this is actually due to like a human running, human walking. So usually the acceleration amplitude is really large, but the frequency is relatively small. Like you can swing your phone like this, but you can't swing it as fast as the earthquake. The earthquake can swing it like maybe 100 times per second, but you can only swing it like maybe 3 or 4 times per second. So that's why like this frequency content actually have the discrimination power. So based on this, we built the we can use these features to tell if the signal is maybe falls here, it's due to earthquake. If it falls here, it's non-earthquake. But you can see there's some overlaps. That means some human activities are very similar to earthquake. We can't totally separate them out. So that's why like using one phone, you may still have like a false positive, which means that the phone thinks it's detecting an earthquake, but it's not. So that's why instead of relying on just one phone, we need to rely on the network of phones. Like if we have a lot of people all say that we detected something like earthquakes, then that might be a real earthquake. So that's why, like whenever the phone detects something like an earthquake, it sends data back to the server. And the server, we can actually implement a clustering algorithm both in time and space. and to confirm this is a real earthquake. So the one we used is modified from like a classical spatial clustering algorithm called DB-scan. So basically, it's a greedy algorithm that starts with each of these like sample in your data sets and use like a radius and number of samples within the radius to determine whether this is belong to the cluster or this is starting a new cluster. So this is an example basically showing you like this is the data you can see. So this is the circle to determine whether this is like in the same basically in the same cluster or it's a new cluster. So we can use this one to determine whether in space and time, we really detected something like an earthquake. So this is what we have done. So we divided the spatial like space into like into these cells. Each of these cells is a 10 by 10 kilometer square. And then we can actually count the number of triggers, like how many phones things is detecting an earthquake in these cells. And we have some like rules to basically, if there's more phones to detect the earthquake in the cell, then this cell light up. So we can cluster these cells and during the earthquake or not, and also like not during the earthquake. So basically during the earthquake, what you will see is that a cluster of cells will light up very fast. And also you can add it to some physics constraint as well, like seismic waves travels at the speed of sound. If something is like a light up too fast, it might be not due to earthquake, but, or like this type of physics constraints. So this way we can actually like automatically find clusters during in terms of like space and time and determine how many clusters do we have. So you can see this one actually finds like this is 4 different clusters because this is too far from each other. So you can have some distance threshold. And so that like if there's 2 earthquakes occur at the same time at different locations, they will not be like aggregated into 1 earthquake. Instead, we're detected as 2 earthquakes. If you want to know more about the details, so we have a paper published earlier this year, have more descriptions of this algorithm. Let me know if you want to discuss more afterwards. So basically, this is the way we can confirm an earthquake. So this is using the real data during Berkeley earthquake in 2018. So this is like a 4.4 earthquake here at Berkeley. So you can see each of these dots is 1 smartphone running MyShake at that moment. So this is San Francisco. Berkeley actually is here. So when you see that like the earthquake starts and then the P wave and the S wave actually propagate out from the center of the earthquake, and now these dots turns orange is actually the dots detected the earthquake. So what you can see that the phone actually detected the earthquake will the seismic wave move away from the epicenter, and then the algorithm will cluster them into different clusters and then detect the earthquake. So this is actually our earthquake detection and estimate the location. And you can see we estimate a magnitude 5, and we actually detected the earthquake pretty fast. And even San Francisco can get about like a 0.7 seconds. But San Jose here, like a lot of the Silicon Valley companies actually here can get about like a 13 seconds warning. So this is like how we use smartphones in action to detect the earthquakes. After we detect the earthquake, we also need to estimate the magnitude. So the magnitude estimation actually is running from, is actually determined by a random forest regressor. So basically you can think it's a very non-linear way that you can estimate the magnitude. So by input the distance from the earthquake, and also the PGA value, which is the peak ground acceleration that you measured from the phone. And then you can actually estimate what's the magnitude looks like from the earthquake, from the data we collected. So in terms of the earthquake detection, as I mentioned, that we only use 2 seconds window to determine whether this is due to earthquake and what's the magnitude and so on, because we want to detect the earthquake as fast as we can. We can wait more time for most in terms of the early warning system. But at the back end, like after the earthquake, we've already had a lot of waveforms we recorded by the phones uploaded to our server. We actually can use much longer waveform to design an algorithm that to determine the waveform is due to earthquake or not, for higher accuracy. So this is actually, we designed a convolutional neural network, basically take the waveform as the image and ask the question whether this is due to earthquake or not due to the earthquake. So basically you can see that these convolutional layers will work as the one we just mentioned, like we extract all types of features, but instead of based on our knowledge what type of feature is more useful, these convolutional layers actually will automatically extract the features from the waveform and then decide whether this is due to earthquake or not due to earthquake. So to give you some example, so these are the earthquake waveforms or the earthquake images input into the convolutional neural network, and these ones are the noise, basically all kinds of human noises. So this is actually the algorithm itself extract the features, what it looks like an earthquake, what is not looks like an earthquake, and determine which one is earthquake and which one is not. It's actually have much better precision and recall in terms of the detection, so or like in terms of the performance. So far we actually have MyShake 1.0 released in 2016, and we released also MyShake 2.0 last year, 2019. So within 3 years, we got like 300,000 people download MyShake. So this is actually the distribution of the MyShake phones for the 1.0. And these users download MyShake all over the world to help us to collect the data, detect the earthquakes, and also like contribute to this community. So we recorded more than 1,000 earthquakes from magnitude 1.7 to magnitude 7.8. So this figure shows you all the earthquakes we detected that have at least one useful seismic waveforms confirmed by a seismologist. So you can see the circle size is the magnitude of the earthquake. The larger the circle is, the higher the magnitude is. And also the color means the depth of the earthquake. So in like this really small earthquake, you need the phones really close to the epicenter, like about 1 or 2 kilometers away from a magnitude 1.7 earthquake to detect the earthquake. But for the larger ones, you can actually detect at further distances. In terms of like the data, this earthquake we detected, we also try to compare earthquake catalog and compare that with the USGS earthquake catalog. So you can see this is the number of earthquake detected. So this is the magnitude, different magnitude bins. So the red ones are the USGS magnitude detected earthquakes. The blue triangles are the MyShake detected. Overall, you see a general trend, but there's a gap because a lot of the events in the ocean actually now detected by MyShake because we don't have phones close by, but can be detected by the USGS using the high quality seismic stations. So this is some limitation that we must see between these two networks. But overall, MyShake actually detected something very similar, like in terms of the completeness. So you can see that USGS's catalog are around magnitude 4.5, and we also see like the detection capability drops at the smaller ones for MyShake as well. So we think that that's a good trend for the MyShake detections. And also in terms of the distances, we can record the earthquake waveforms. So this is actually from the real MyShake data. So you can see from smaller ones to magnitude 8. So all the ways we detected, all the dots are the ones we detected with the waveforms. So we actually can get a theoretical limit of the distance we can record the earthquake waveforms. For example, a magnitude 6 earthquake, we can probably see waveforms at about 350 kilometers from the phones. But because these phones have different qualities, so it really depends on the quality of the phone, the sensor inside the phone. But overall, we see like a larger the larger the earthquake, so we see the further the distance that we can detect it. And also we can use this data recorded by smartphones to do some seismic network operation, for example, determine the location, distance, location, time, magnitude, and so on with of the earthquakes with the phone data, and also get very nice results as well. So this is all published before. If you are interested, like I can point you to the papers. But also like this is a waveform, seismic record section wave, basically from the waveforms of all the phones we recorded during a magnitude 5.2 earthquake in California. So you can see the propagation of the P wave and the propagation of the S wave from all these users' smartphones. So each of these trees is one smartphone recorded at different distances from the earthquake. But basically you can see for the P wave, we can see this about like 100 kilometers. But for S wave, we actually can see at about 200 kilometers for the recordings of the earthquakes. And also in terms of the quality of the recording, so this is comparing the MyShake recordings with the nearby seismic stations. So this is actually about 40 kilometers from the earthquake, and the sensor from the MyShake and the sensor from the traditional sensor is about 1 kilometer apart. So overall, you can see the P wave here, the S wave starts here, and the general shape actually are matching very well. And in terms of the amplitude, MyShake seems to have like a more higher amplitude. So at 100 kilometers away from the epicenter of the earthquake, what you can see is that the seismic stations recorded the P wave part, but due to the noise on the phone is so high that we didn't see the P wave parts. We only detected the largest shaking amplitude part, which is the S wave part. So this is like this is like the limitation of the using the smartphones, because the sensor quality are not comparable to the high quality research grade devices. But still we can record the earthquake at further distances for the S wave part. For the early warning purposes, actually it's also useful. This is some of the smaller earthquakes we detected on the different phones. So basically, this is like a core blast actually in Bay Area here. near the Silicon Valley, and one user is about like 7 kilometers away. We actually recorded this query blast on the phone. And also this is a magnitude 2 earthquake actually recorded at about different distances, but all less than 10 kilometers. So the red one here are showing one of the seismic stations nearby, but overall you can see it can record this signal, but due to the high noise on the phone, it's also like the signal noise ratio is relatively low. So all these are from the MyShake 1.0. And last year, we actually released MyShake 2.0, which have a new user interface design, especially designed by some like UI experts. The reason is that one thing we want to do research, but the other thing is that we need to serve the community and let our user to continue use the app. Let me just see what's the time, make sure I'm good on time.
It's okay. We're quite flexible, so
okay,
don't worry.
Sure. Yeah, I will try to like finish like within the next 10 to 15 minutes, so that's leave a few minutes for questions. But yeah, feel free to stop me if you have any questions. So this new version of the app gives the user more functionality. So first of all, it starts to sending out the early warning messages. Whenever there's an earthquake nearby in California, it will give you a warning. Sometimes the warning arrives before the shaking even starts at your location. But this is right now, it's actually from the shake alerts early warning message, which is basically using the high quality research grade seismic stations to generate this type of alerts. We are also working on to integrate the MyShake data as well into the system. So we are also asking the users to fill out the felt report after the earthquake, like whether you felt the earthquake or not. After the earthquake, you can basically do a very simple survey and then show after you submit your survey, it will show like what the shaking looks like at various locations, how many people felt this earthquake in each of these bins. So this gives users a way to see like whether there's large shakings around them by like by the evidences from other users. And also we give users more preparedness and safety tips so that for them to prepare better for the earthquake hazards, and also gives them more real-time earthquake information around the globe so that they are on top of the earthquake information. So these are the all new design of the app. And also this is one of the example from actually about 2 months ago now, 4.5 earthquake in the LA region, so Southern California. So the earthquake is here, and this is the zone actually we warned people, we send out the early warning messages. So you can see the ice wave actually arrived to this circle here about 15 seconds, and we send out the early warning messages to 20,000 smartphones in this region, and about 50% of them are actually within 2 seconds got the warning in terms of the latencies. So overall, like because this is a smaller earthquake and also occurred in the densely populated area, so most people probably like here, they already felt the shaking when they arrived, when they received the message. But the people around here, they get a few seconds warning before the shaking actually starts at their locations. So this is like a real test for MyShake actually sending out the alerts. But also, like I mentioned before, that right now I'm a visiting researcher actually at Google, basically to help them to turn this concept or turn this prototype into a global scale earthquake early warning system using all the phones that have the Android on the Android platform. So this is what we actually worked on, and we launched actually two products during the August 11th this year. So the first one is that we actually send out alerts to all the Android devices across California from the Shake alert system. And the second part of this is actually the same 4.5 earthquake I just showed here. So you can see MyShake seems like we need the users to download the app. So we only send out to 20,000 phones, but for Google's alert for the same earthquake, we actually warned about 2.2 million people within the region, which is really impressive. And the second part is like the phone, like the detections using the accelerometers inside the phone. So right now we are still working on that to deliver with the goal to deliver the alerts around the globe, especially at the places where they don't have earthquake warning system. So this is like a big team actually at Google. So I won't read out the name here, but this is all the team members actually at Google working on this product. So to give you some more information, so this is actually using the phone detection from all the Android phones during the magnitude 5.1 North Carolina earthquake this year. So you will see like each of these dots are the phone triggers during the earthquake. So this is like the earthquake occurred here, the P wave and the S wave. You can clearly see all these like the phone triggers are based on the wavefronts propagate across the whole region. So you can see this again. There's so many phones that triggered, like you can even trace out the S wave wavefront based on these triggers of the phone. So if we plot all these phones, so this is actually the distance from the earthquake. This is the time from the earthquake. So what you can see is the like a very nicely triggered phones actually form like traces out the seismic waves. If you were in a class like in seismology, you will know that there's a P wave, S wave, and also like some of the later phases as well, like the SMS, SG, and so on. So all these phones are actually traced these different phases very well. So this is the beauty of a very dense network that using the smartphones. And also, I won't go into the more details, but also like just to give you more examples here. This is the Berkeley event, actually Pleasant Hill event that occurred not so far from Berkeley, that you can see all these like different triggers of the phones. And also like this is the one, it warned 2 million people, and you can also see the triggers of these phones in the region as well. So this is a magnitude 4.7 event in Tokyo, and that recorded like on massive phones. Basically, when the seismic wave travels across the region, it triggered all the phones in the region. And also, not only to record some like natural earthquakes. In January this year, there's also explosion from Houston in US here. So what you can see is this clearly line here, which is showing the propagation of the acoustic wave actually in the air. So this is the P and S wave. You can see this one is much slower. And if you estimate the wave speed, so this speed actually is the sound speed. It's about like 340 meters per second. So basically this is the acoustic wave that travels across the air that's recorded on all these like Android devices. So also we use machine learning like the convolutional neural network to try to estimate which one is P wave, which one is the S wave. So what you can see here is that like we can estimate the green ones are the P wave triggers, the red ones are the S wave triggers, and also the blue ones are the noise based on our classifier analysis. But you can see there's still some of these are like falsely determined as S wave, but it might be like due to the P wave. So still there's room for improvement. And also like try to understanding the ground motion is more important in the Android devices, because what we found is that, so this is like a distance from the earthquake. This is the amplitude from the earthquake. So what you can see that, so basically the traditional seismic network records the shaking amplitude like this, like it's decay here. And the Android phones actually have a higher amplitude. So we are still trying to understand what this means, like why the Android devices actually recorded more higher amplitude. Is that due to amplification, or is it due to the response from the table or response from the building and so on? And understand better of this relationship or these responses will help us to estimate the magnitude and also generate like the shape maps better in the future. So because you can see there's only like these red dots are the seismic stations from the traditional seismic stations, but there's much more phones that if we can use this, we can have a very high resolution shaking intensity map across the region. So that's the beauty of it. So I will stop here because I think it's also almost the time for this 1 hour. And also, if you are interested to contribute or if you are interested to collaborate on MyShake, let me know. This is still a lot of ongoing work at both Berkeley and also at Google to make this really work in the future. We hope that in the future we'll have a global scale seismic network that using only the smartphones. Okay, thank you.
Okay, thank you very much for your talk, Qingkai. And now it's time for questions. So for the audience, feel free to open your mic. And before you ask a question, please let us know your name and your institution. So go ahead.
Yeah, I can't see you guys. If you can turn on the video, that would be great, because it's always good to have like a in-person communication.
Yeah, I agree. But the problem is that many people probably are still on their beds.
Okay. Yeah,
they're reluctant to share that video.
Yeah, you guys are really great to do the seminar on the Sunday morning.
Yeah, I think that's one way to work it out, I suppose, because if something occurs at 9, people on their bed, they watch for a 1 hour video and then get up, then they could do other things, spend the rest of the day somewhere else. Okay, actually, I have a quick question for it. So actually, I just checked out my phone and I found that I used to download the Quake feed, which I think it updated the news, the information of earthquakes that with the source from USGS. So my question is that is the MyShake the only provider in the world that are trying to use the smartphone to detect earthquakes, or do you have any other competitors?
No, there's others as well, right? Like Google right now is actually doing their system. Basically, all the Android phones will have the earthquake alerts and earthquake information in the future. And also there's some other groups, like I think in Europe and in Taiwan, also doing similar research that are trying to use the smartphones to detect the earthquake and to do earthquake warning. So MyShake is one of them that trying to push this forward. I think there's a lot of challenges you can see in the data we recorded, like a high noise and a lot of the times you don't know the user, what the user is doing, and all these challenges that translate into the system stability and also reliability. So that's what we need to address. I think if you are interested, you can definitely search online to see other people's work. They may different from MyShake, but a lot of the basic like idea or the concept are very similar. Basically use the accelerometer to detect the earthquake and then warn people before the shaking starts.
But are all the information shared between the different apps? So do they share the same database? Okay.
Yeah, the reason is that like this is actually very sensitive, not like research we can easily share results. A lot of these ones are like have privacy of the users, like because you want to use the location of the users to determine the earthquake and all these things. So that's why it's actually very sensitive for the data to be shared with others. And also a lot of the times the data actually are, we have done a lot of ways or actions to blur the data so that you can't get the precise location. So like the ones I showed you, a lot of them are already added the random noise into the location, which is like basically showing you the a fuzzy location view of the phones to protect the privacy of the users.
Yeah, actually, this is my next relevant question for it. So if the user, for example, me, if I download the MyShake, does that mean that I will keep all my, like, basically you record all the data of my motions, or either is a non-earthquake motions or earthquake motions. Then although is the noise that you mentioned about that really complicates, or you try to separate non-earthquake to earthquake noises. But from the non-earthquake motions, that could also correspond to like the different activities people have been doing. Basically, as the time goes by, I think with the more advancement of the algorithms that could categorize my actions to a certain extent, not only knowing where I am, but knowing what I'm doing. So basically, I'm being monitored and being tracked. So is that the risk when the user download the MyShake 2.0?
Yeah, for MyShake right now, if it's quantified as a human activity, that data will be the waveform data basically will be ignored and not uploaded to the server. So we try to protect the users from this way. We only upload the data that the algorithm thinks it's due to an earthquake. So if some other human activities are correctly classified, we will just ignore the data. But you know that some of the human activities are similar to the earthquakes, that if the algorithm thinks it's an earthquake, then it send the data to the server. Yeah, but right now we're only collecting the earthquake related data if we think the algorithm thinks it's due to an earthquake. Yeah.
Okay. Other questions from the audience?
Yeah, feel free to ask any questions, even questions not related with project.
Can you hear me?
Yeah, I can hear you.
I'm Wang Huihui, and I have a question.
Which is your institution, Huihui?
We know that the human body is a good buffer. So when we use a phone with ourselves, not on the desk, the signal of the seismic will be much more lower. Will this be a problem for the sensor?
Yeah, that's actually a good question. It definitely will be a problem. Like if you are having the phone on your pocket while walking, running, so your body actually is a very good damper. It will damp out a lot of energy. So that's why in MyShake there's also like a very simple algorithm to determine whether the phone is in steady mode on the desk. So right now we are mostly using only the phone, only the waveform from the good seismic records rest on the phone. rest on the desk. So that's why you can see the algorithm actually quantifying, like if this is due to human activity, walking and running, we will just ignore the data. We will not like record any of the data from that on the desk. Then we actually upload the data to the server. So for sure, that data is definitely, if in the future it might be useful, but right now we are filter that out. And also like we think it's too complicated to try to study the damper of the human body. So that's why right now it's all like filtered out, yeah.
Well, thank you, Professor. But I really love this idea. Yes, I love this idea more than any girl. Thank you.
Sure, yeah. Then you can continue working on that as well.
Yeah. So that was Wang Huihui from USDC, University of Science and Technology of China. Okay, so do we have more questions from the audience?
Yeah, if you have questions, feel free to ask me or send me email as well. I'm happy to answer some questions as well.
Or you could type your questions in the chat and I could read it for you.
Let me stop sharing. I see the question. Can there be any?
Yeah. Please read it, Qingkai.
Sure. Yeah, I see the question from Aka, right? Can there be any variability in recorded data based on the material of the phone, like two phones placed at the same place, however the material is different? So I'm Aka from, I actually don't know how to pronounce
Jadavpur. Yeah, Jadavpur University, India.
Okay.
So that's a question for Aka. Yeah.
Sure. Yeah, that's actually a very good question. So the Android phones are known as like have a very broad spectrum of qualities, like a high-end phone, low-end phone. So for sure, they have very different responses. We already found that. So in fact, we also have a paper actually try to document this, like the different have a different noise level, different phone have different responses. Right now, we haven't done large-scale analysis on this yet, but it is true that different phones will have different responses, even at the same places. But in terms of the detection and for the earthquakes, a lot of the times we found that variability actually not affected too much of the detection. It has some effect on the amplitude, and like even two phones at the same location might record slightly different amplitude of the earthquake as well, due to the sensitivity. That's why right now we do have some research going on to study the variabilities of these phones, but right now we don't have a good way to really quantify this. All we can do is to quantify from the data we recorded from the different type of phones. Actually, right now I have a PhD student working on this problem, try to modeling with the different brand make of the phone and at different countries, what type of response we are actually expecting to see, and also whether we can model this into a statistic model that we can actually use it in our real-time system to automatically quantify the quality of the waveforms from the different type of the phones. So she is actually working on this problem. She actually got some results. Hopefully we will share, we will have a paper out in the next few months to show you the results, yeah.
Hi, this is only a postdoc from the South University of Science and Technology. I have a silly question. I just wondering what the quality of the waveform like. I see you have a lot of the phones, and you have the probably some phones just stable, probably can record some good waveform. I was wondering, can we use those waveform to obtain some, do some further analysis, for example, like obtain some structure information of the Earth, like even though it's just a single analysis, that would be interesting.
Yeah, that's also one of the research that we are doing. It's actually not a silly question at all. It's some questions that actually we are also really working on. We try to see what kind of seismological applications we can do in terms of like study the structure. It's a little bit hard because the phone, these type of sensors are only good, like the frequency content is only good to about like 10 seconds. If 5 to 10 seconds, if you think to go to like a lower or like a lower frequencies, it's actually very hard for this type of low quality sensors. So that's why we think the usage will be limited in that type of study, but still there's like probably like around like 5 seconds you can still have very good signal out. In terms of other applications, we actually use the data. We can actually do the stress drop. We actually try to see if we can like do the moment tensors and all these different or like a routine seismological applications. So far, I can tell you that if you have enough phones in the region, so you actually can do a lot of these like typical or routine seismological applications. But for the very high precision or like the application that needs like really good quality waveforms, that's probably like out of the scope of the phones. Yeah, the phones are low quality sensors, which is only $2, probably like a $2 each for the sensor. But for the research grade sensors, like usually is $20,000, which is like a huge difference. You can see why. You can see from the price that the quality of the recordings. But we think that like another way to deal with these qualities, that if you at one location you have many smartphones, you can get some of the stacking methods to improve the signal as well. But so far we only showed promising results in some of the like the experiments that we put the phone at one location and then stacking them to extract some like a fundamental frequencies of the buildings and so on. But in reality, it's much more harder because we don't know the user's location. We don't know the user's like phone's heading. We don't know like where they put the phone and so on. All these are the factors that contribute into the uncertainties of the waveforms we recorded from the users. Yeah, and also you don't know the covers. They are whether the phone have a cover, whether the phone has something else. Yeah.
Yeah, I agree. Thanks so much.
Sure.
Okay, I think that's so much for today. And thank you very much for sharing, Qingkai, and also thanks for our participants. And this video will be uploaded on Bilibili and YouTube. So some of the other people interested on this could feel free to watch it. Okay, with that, thanks everybody again, and have a great day.
Sure, thank you.
Evening.
Thanks.